All right, so now we are ready to look at Module 5. Okay, so Module 5 is all about equilibrium of rigid bodies. We've already looked at equilibrium. We did it of concurrent force systems. And if you remember, a concurrent force system was a force system that shared either the same application point, or if we extended the forces along their line of action, they would have a common intersection. Okay, so that was Module 3, where we had equilibrium of concurrent force systems. And the big deal there was we summed our forces in the X and Y and we set it equal to 0, okay, because equilibrium meant that everything balanced out. Now we're going to be looking at rigid bodies. And now we are not going to have forces that are going to all intersect at the same point. They're actually going to be offset distances. Module 4 was preparing us for this because we learned about moments and offset forces in Module 4. We're now going to use them with the condition of equilibrium here. Okay, so as we look at Module 5 learning plan, we are going back to the McGraw-Hill ebook. Now, not to confuse things, we had Module 4 and we had Chapter 4 handout that you guys had from a different resource that I had. Okay, they didn't do the moments like I would have liked them to. So I pulled it out of a book that I used to teach out of that's no longer in print, unfortunately, just in the last couple of years. But I pulled it out of there. So that was Module 4, Chapter 4 handout. Now we have Module 5, Chapter 4 in McGraw-Hill. So I don't want to confuse things. So really, if you would, for these two modules, they're out of Chapter 4s, but just make sure that you keep straight. Module 4 was the handout, Chapter 4, and Module 5 is McGraw-Hill, Chapter 4. Okay. I know you'll keep it straight, but it's worth talking about, especially if we have people finishing up Module 4 and then starting Module 5. You'll notice that here are those guided notes. So if you're in class, I haven't printed out it for you. This is going to be what we're going to be handing in for our practice problems. And these are the problems that we're going to be going through demonstrating in class here. So we'll be doing that. Oh, this hung around from previous. We are not doing any Connect assignments out of the McGraw-Hill book. So don't even worry about that. There's nothing assigned for you. I'll fix that up, but you will have the practice problems and the application problems, just like we have for the previous modules that we've been looking at. So those are there. Then you'll notice that there's the practice problems. This is where you'll be handing in. And then application problems, we have quite a few. Module 5, I believe, is probably the most important module that we have in statics. Okay. So that's why I want to make sure that we spend enough time on it and that you get a lot of practice. Okay. And that's what we have here. Through the time that we have together, I know we'll get started on some of these homework problems as well as doing the sample problems. So you have what you need to be able to do those. So with that, what I'm going to do is I'm opened up to chapter 4 in my book, but I'm going to primarily look at our guided notes. So I'm going to go back underneath my camera here. I'm going to turn this down, zoom in a little bit. Focus. All right. So we're starting on page 157 in your McGraw-Hill ebook if you wanted to follow along there. But like I said, I'll kind of be pulling the illustrations out as we need to, but then really referring to our guided notes here. Now, as we get started here, it says, when forces in a body are in blank, all the forces and moments are equal to 0. Can you guys already imagine what the word is that's going to go in that blank there? Equilibrium, exactly. So equilibrium is going to go here in that blank. So when forces and a body are in equilibrium, all the forces and the moments on that body are equal to 0. There are 3 equations of equilibrium. We already have used and practiced 2 of them. So those 2 are sum of the forces in the x equals 0, sum of the forces in the y equals 0. And then the last equation now is going to be sum the moments. And I'm going to put a little cloud here. That's going to reference the point that we're summing around. So we have to identify the point that we're summing around, just like we did in Module 4. And we're going to set that equal to 0. Okay. And then draw the convention. So we know, and I'm not going to call it I guess it's really not the new convention anymore. We did add the rotation, but now it's a complete convention, if you would. So this lets us know that when we are writing our equations of equilibrium, why we're giving positives and negatives to the different values, okay? Now, we've already been drawing some free body diagrams, okay? So you have a little bit of experience with this. We're going to continue to do this, but can you tell me, and I'll open up the chat book or the chat box because I want to make sure that those who are virtual get a chance as well. But what things do we want to include on a free body diagram? I'll start with the first item for those in the room. Anybody want to chime in? What's one thing that we were going to find on a free body diagram?
The axis?
Sure. The axis system. Okay, number one, axis system. So like the X and Y?
Yeah.
Right? Okay. Virtually. Oh, I've got vectors. Gabrielle said vectors. Absolutely. So vectors are going to be the forces that are represented, right? So I'm going to put vectors, forces. Good. Brooke, you had your hand up. Units, absolutely. So we have to make sure that when we identify our vectors or when we have any distances, we're going to have the proper units on things. What else? I'm going back to virtual. Does anybody want to chime in with another item that we're going to show on our free body diagrams? Forces, vectors, we got to have the axis system identified. Something starts with a C that you have to have on every problem, and it's part of your free body diagram. Starts with a C. Convention, yes, you're going to have to make sure that we have a convention. Okay. Is it S or I think it's T? We're going to do one more. There's one more that I'm thinking of virtually. Who can think of the last thing that's on here? If I have my forces, what was that?
Labels?
Oh, okay. We're going to do 6. Yeah, labels. We have to have labels on all of our items. Yep. Okay, good. So is it F1, F2, F or an A or B, a C, right? Excellent. One more that I'm thinking of specifically. Starts with a D. Then an I.
Dimensions?
Oh, close. Distances. Distances. So whenever we have distances that are in between things, we want to make sure that we have those as well. So distances. Good. Good, good, good. Did anybody think of anything that we didn't mention yet? Okay. All right. Now, the next thing that we're going to do is we're going to look at section 4.1a. And on page 160, we have some supports, okay? So as we start looking at the different problems that we're going to be solving, you're going to notice that they're going to be like things that we see in real life. One of the things that we're going to be looking at early on here with one of our sample problems is looking at a tractor and it's lifting something and what are the reactions going to be at the wheels. A wheelbarrow, we're going to have some, a load inside the wheelbarrow and somebody's going to lift on the handles, but it's also going to be, supported by the wheel in the front. So we're going to have to be able to translate from those real world applications to how are we going to represent this on our free body diagram. And supports, standard supports are going to be things that are going to come up quite often. So what we want to do is we want to get familiar with the most popular types of supports that we're going to be seeing and how to then represent them on our free body diagram. And that's what page 60, this illustration right here, it's a table and it's actually figure 4.1 on page 160. So it's something that you're probably going to want to go back to every so often to just confirm what you're doing. The first one that we have here is a kind of a category called a roller support or a rocker or a frictionless surface. Any one of those are going to have one force perpendicular to the surface that it's riding on. Okay, one force perpendicular to the surface it's riding on. A very popular one is a roller. We're going to see this identified in many of the problems. Now, the reason that there's one force supporting perpendicular to the surface that we're riding on is that it's free to move, if you would, as we look at this surface horizontally, because it's on wheels, right? So it's going to freely move horizontally back and forth, left and right in this case. But whether it is where we have the rollers on the bottom here and they're in contact with the surface that it's riding on, it has to have contact to support. Or if it's captured maybe between a, above and below type of a situation where it's rolling in between, this has to have contact. So in either one of these cases, in a roller, there's going to be one reaction perpendicular to the surface it's riding on. If that surface is at an angle, then we got to figure out the components, okay? But in the case of a horizontal or a vertical surface, it would simply be then, vertical or horizontal. So one force. So if we look here, oops, nope, not yet. The next one that we have, let's look at this first, and then we'll go back to our sheet. I have them in a little different order. The next one that we have here is a cable or a link. A cable or a link is going to have its reaction, its support along that cable or link. Now, in the case of a cable only supports when it's in tension. So if this is in tension, it's supporting. But if it collapses and it is in compression, that cable is no longer supporting. Okay, so we only pick cables for situations where we anticipate it's always going to be in tension. But if we have a condition where it's maybe a similar type of a situation, but there are times when it can be in compression, then you'll notice that we have a rigid link, because that way it can be compressed or it can be in tension or pulled apart. And in both cases, it will still do the supporting that's required. So the key here is that the force would be along that link or cable. And then if it's at an angle like we see here, as you can imagine, then we would have to resolve it into components, okay? The next one here, this one is a frictionless pin in a slot. Not that it's not used, but we aren't going to be seeing applications of this in this particular unit. But you're going to notice that it's going to be perpendicular to the sliding element. Okay, I think we see this. I want to say in kinematics next fall we'll see applications of this. The next one that we have here is a pin connection. Probably the roller and the pin are the two that we're going to see most often. The pin connection, because a pin is going through the middle here, now we do not have the ability to go horizontally anymore. So with the pin in the middle here, this is now constrained. It can't go back and forth and it can't go up and down. So it will always have an X and a Y reaction. Okay, so it's similar but different than the roller. The roller only has a support perpendicular to the surface it's riding on because it's free to move back and forth in, if you would, the X direction. But when we put a pin in place, now it's constrained and it's not going to be able to move in those directions. Okay, so it supports in both directions, X and Y. And then the last one that we have here is a fixed support, or sometimes referred to as a cantilever beam if it's horizontally oriented. In this case, there are three supports that we're going to have. We're going to have an X, a Y, and a moment at that support, because it's gonna act kind of like a diving board, and it's going to want to rotate on that support. So we will do some problems where we'll see the application of a fixed support or a cantilever beam. So the four that we're going to see most often are going to be rollers, cables and short links, pins, and then fixed supports. So if we go to the bottom of our guided notes here, you'll notice here that I want you to fill in the blanks. So common supports in their ability to react to applied forces. For pins, we're going to have two reactions, an X and a Y. That's the frictionless pin that we saw earlier. Rollers are going to have one reaction perpendicular to the surface it's riding on. Okay. A frictionless surface, we're going to find that a frictionless surface is in the same category as a roller, okay? And that's going to have one support perpendicular to the surface that it's riding on. Cables, it's going to be one reaction, and it's going to be along the line of the cable, and it'll be pulling away from the body because it'll be in tension. A rigid link will also have one reaction along the line of that link, either pointing towards or away, because in that case, a rigid link can actually support in its, if you would, compression mode. A fixed support is going to have three reactions. X, Y, and a moment. And then we have a friction surface. Now, we didn't specifically look at that, but it's in the category along with the pin. And you'll notice here that when we have a rough surface, this does have, if you would, resistance because it's a rough surface. So in some cases, you have to overcome that in order to get it to slide. So that would be considered also two reactions, one that's going to be perpendicular to the surface it's riding on, and then one that is going to be opposite the impending motion. We're not going to be looking at friction in this module because we have a friction unit right at the end of this class. So that'll be something that we end statics with. So we'll see friction applications there. Okay, so that's page 160. We'll actually might keep this out because we'll probably reference it when we do some problems. So most of your problems you'll be solving for unknown blank and blank at the supports. What will we be solving for? For most problems, you'll be solving for unknown reactions and forces at the supports. All right, so there's going to be a process that we're going to go through here. All right. Now, in all of the problems in Module 5, the assumption here is that we are in equilibrium. That's the overarching subject that we have here in Module 5. So that means that we are always going to have our conditions of equilibrium here. Some of the forces in the X equals 0, some of the forces in the Y equals 0, and some of the moments around any point that we give are going to be equal to 0. Everything. So we're going to start by drawing our free body diagram. That's what FBD means, free body diagram. And we're going to add our, what do you think goes there? Convention, absolutely. Remember, I changed my rules. I want you to start each problem on a new page. I don't want you to continue on a page with any of the problems that you do. Make sure that you have a convention at the top of each one of your problems, not like for a problem set. And number 3, something that I've been noticing when we have problems that go to another page, I'll have like a random page and I'm not sure what it goes with when you guys hand in your homework. So then make sure if it does go to a second page, just tell me it's problem blah, blah, blah continued or something like that. That way it helps me to line up when you guys hand things in. So convention on each one of your problems. Again, free body diagrams, add all the forces and applied loads, any known magnitudes, unknown variables, dimensions, add all the reactions at the supports, identify the type of support, add vectors to represent, and then assume a direction. Sometimes when we're representing our reactions at the supports, we might not know exactly what direction that force is going to go in, but we're going to assume a direction and I'll let you in on how we will know or how we'll confirm if it was right or not. It says use blank, 3 words, to solve for any unknown applied loads and reactions at supports. Use the equations of equilibrium. Okay, use the equations of equilibrium. Okay. So we're going to start each problem with some of the forces in the X equals 0, some of the forces in the Y equals 0, some of the moments equal to 0. All right, so we are going to start by doing a problem, okay? And I picked problem 4.2 in your book. It is on page 174. So we're skipping over some of the sample problems here because I felt that 4.2 looked like a good problem to look at, okay? So 4.2, we have a 2,100 pound tractor is used to lift 900 pounds of gravel. Determine the reaction at each of the 2 rear wheels and front wheels, okay? So you're gonna notice here we've got the tractor, back wheels, front wheels, and then here's the bucket that has 900 pounds coming down. And then you're gonna notice that there is a G. That G represents the center of gravity of this tractor. They mentioned in the problem statement that the tractor weighed 2,100 pounds. So what it's telling us is we have to not only account for supporting that load out here, but this tractor at the wheels has to also support the weight of itself, okay? Sometimes weight is negligible. And so if they don't mention it in a problem, you don't have to worry about it. But if they mention it, then we have to worry about it, okay? So we're going to be adding in the 2,100 pounds there. Now, free body diagram, just like any other free body diagram that we've drawn up until this point, it's a simplified version of. So we're going to do a very simplified version of our tractor here. So to represent this, I'm going to get out my straight edge so it looks nice and you guys can follow it. Okay. We are simply going to draw a straight line, okay? So my straight line, I can do right about here, okay? I don't want to forget my convention. Make sure that you add the rotation going counterclockwise is positive as well. Now, in our problem, this is what you always want to look on your problems as well. Are there identified points already? So in this case, they're calling the back wheel A, front wheel B, and they don't really have anything else. They do have G there, but that means that I want to make sure that identify points that are already given to me. Don't make up new variables for points. Does that make sense? Use what's there first, and if there is something that you need to add, then you can add that. Then here, I'm going to put point B, and then I'm going to call the very end C, and that's going to be where I'm going to put my 900. And then we are going to be putting right about here-ish. This is going to be G, okay? Now, we have some distances here. We have 20 inches between A and G. We have 40 inches between G and B. And we have 50 inches between B and C, okay? So that's adding my dimensions. Now I want to represent, first, I always like to put, if you would, what they call applied loads. So the first applied load, if I look at my diagram here, the obvious one is going to be the 900 pounds that's going to be going down. So I have that identified here at C. Okay, so this is going to be 900 pounds. Okay. The other one that we would show here is going to be the 2,100 pounds. This is the weight of the tractor. So they're not showing it here. We know that it's going to act at G, but we also know that any weight is always represented going down, right? And that's going to be 1,200 pounds.
That was 2,100.
Oh, you are correct. Thank you. Thank you. Thank you. 2,100. Yep. Thank you. Yep. Always put eyes, always check my work here. Talking at the same time of doing, it's harder than what you think. Not really. All right. Now A and B. A and B are our two wheels. Okay. Now, if we look at our list here of common types of supports, that's where the support is for the forces that we have for the weight of the tractor, as well as that 900 pounds on the scoop. Which support here do you think looks like it would be similar to the wheels on our tractor? Jacob, say it louder. The rollers. Yes, yes. So rollers, they allow, if you would, in this case, horizontally back and forth, right, to move freely, but it's going to support perpendicular to the surface it's riding on. So each one of those tires or wheels are going to be a roller support. So we are going to show it with one force perpendicular to the surface it's riding on. It's riding on a horizontal surface. So that means that the reactions, this is what we call the reactions at the supports, are going to be at A, okay, in the Y direction going up, perpendicular to the surface it's riding on, and at B, okay? Now, I have points A and B identified here, but I'm going to call this force AY and this force BY, okay? Because they're going in a vertical direction. So you want to call the actual force a number or give it a label. So now that I have these called out, these are my two unknown reactions at the supports that I'm going to try to find using the equations of equilibrium. And those are usually the most common problems that we're going to have. What are the reactions at each one of those wheels in the front and in the rear? So step number one, this was my free body diagram, okay? So now step number two, as it says here, we're going to use the equations of equilibrium, okay, to solve for my unknown reactions, okay? So my two unknown reactions are AY and BY. I have three options for my equations of equilibrium. I'm going to write them out here. So I have sum of the forces in the X equals 0, sum of the forces in the Y equals 0, and I have sum of the moments around a point, that's my little cloud, also equal to 0, okay? So through the use of these three equations, we'll be able to find those unknowns. Now, sum of the forces in the X, let's look there first. Sum of the forces in the X means that we're going to look at the forces that are in the X direction. Do I have any forces in the X direction? No. So in this problem, we just won't use it. Okay, that's all. You don't have to even list it. I just put it there so we could see we have three as options. But in this case, we will have problems where there are X's. Don't worry. But for this one, there aren't. So we don't have to worry about that one. So we're down to two equations of equilibrium. Sum of the forces in the Y. So just like we did it for concurrent forces, we're going to do that very same thing. So I'm gonna rewrite it down here. So sum of the forces in the Y equals 0. Okay. And now on the, remember, this is an equation with two sides. On the left-hand side of my equation, I'm going to write out the forces in the Y direction. And on the right-hand side of my equation, I'm going to set it equal to 0. So left-hand side, I'm going to start left to right here on my diagram. I have an AY. It's going up, so according to my convention, that's a positive value. My next force is 2100. I'm going to put a minus in front of that. Tell me why I put a minus in front of it. It is going down, exactly. So according to my convention, that's a negative value. So negative 2100. Move along. My next force that I have identified is BY. Positive BY. I have it going up. I assumed an up direction. And then lastly, I have a negative 900 pounds. Notice that in this equation, I added the units. All right. Make sure I don't want to see 2100. I want to see 2100 pounds. Okay. 900 pounds. Now, this is the left-hand side of the equation. This is the sum of the forces side of that equation. What you need to do at this level, and I look at this and I'll take off points if you don't do it, you have to set this equal to 0. This is an equation of equilibrium. It has an equal sign and it has two sides. One side is 0 and the other side is numbers, okay? So now what we're going to do is we're going to combine what we can and then see if we can solve. So you'll notice here that we can combine the negative 2100 and the negative 900. So I'm going to have AY plus BY minus, that would be 3000, right? Equal to 0. And then if you wanted to get rid of the negative, we can say AY plus BY is equal to 3000 pounds, right? But that's as far as we can go because there are two unknown variables. All right. But all is not lost because we still have summing moments. Okay. So we're going to sum moments around a point. Now, this is where you got to be strategic. If I know that the force at A and the force at B are the two unknowns that I have, I'm going to sum my moments around one of those points because when I put my finger on one of those points and I push in the direction of that force, does that cause a rotation? No. So it's not even in my equation and it eliminates one of my unknowns so that when I get to the BY, that ends up being my only unknown. Okay. So that's how you kind of determine where you're going to sum around. It's going to be on one of those unknown variables. Make sure you don't have more than two, and you shouldn't. So we're going to sneak down. I'm going to leave a little bit of room here because we'll probably come up and we will, fill some more in. So the next thing I'm going to do is I'm going to sum my moments around point A. You have to tell me what point you're going around. You're going to set that equal to 0. You have to show me sum of the forces in the Y equals 0. Sum of the moments around A equals 0. If I don't see those and you just start, randomly putting numbers, then points off. Okay. It's kind of like you're telling me what you're going to do. Then down below here on the left-hand side, we're going to sum our moments around A. So we're going to put our finger up on A, eliminates the AY as we already said, but then we're going to go to the 2100. We're going to rotate in the direction of 2100. It does cause a rotation. That rotation is clockwise. The offset is 20 inches, the perpendicular distance, right? So I'm going to start with parentheses. Remember, all of your moments have to have parentheses around them, okay? So this is going to be 2,100 pounds times 20 inches. That's my distance from A, perpendicular distance from A. And out front, I'm going to add the negative value because I'm in moment mode, if you would, which means that I'm looking at the direction of rotation. And when I have my finger on A, this rotates clockwise. So negative out front. The next moment I'm going to have offset force is going to be BY. The direction that I assumed BY is going up. So when I rotate, it's going to be going counterclockwise, which will be positive. And its offset distance is 60 inches. So I'm going to start with my parentheses. BY is the magnitude of the force times 60 inches. And I'm going to put positive out front because it's a counterclockwise direction of rotation. The last force that I have offset is the 900. I'm going to rotate in the direction of 900. That's going to cause a clockwise direction, so that'll be negative out front. And I'm going to have 900 times 60 plus 50 is 110, right? So this is going to be 900 pounds times 110 inches. And then out front is going to be negative because that's a clockwise rotation. Okay. Am I ready to solve? No. What do I need to do here?
Multiply.
Nope, I don't need to multiply anything. I've got to finish this line. What do I need to
Equals zero.
finish this line with? What?
Equals 0.
Equal to 0. Thank you. Thank you. Yes, equal to 0. Now I'm ready to. Don't randomly add the 0 and don't randomly, I see students try to sneak in BY is equal to, but they never did this. I'm like, no. No equation there. We need an equal sign and two sides. Okay. All right. So now as I look here, I have one unknown. I have algebra. So I should be able to solve for this, right? So go ahead and solve for BY. I'll do it over here too. Couple things. Number one, notice that I have BY is equal to, and I've got the number with the units in back of it. So when you put a box around a final answer, because we're trying to find the reactions at the support BY here, okay? I want to see BY is equal to, don't just put a box around a number. Sometimes I see students do that. And also make sure that your units, your final units. Now, As you can see here, I pulled my units all the way through. I use the symbols in the top one mostly because that's usually the longest line for me and the symbols keep it a little bit shorter. But then you're going to notice I put the pounds and the inches, I write them out as we go along. Notice that they stayed along with each one of the quantities. So for instance, the 60 inches times BY. Then when I divided 60 inches underneath, the inches canceled top to bottom, and I was left with pounds for a variable that is a reaction force, okay? So right away, if I end up with the correct units for the variable that I'm solving for, again, it lets me know that I probably set this up correctly, okay? If I would end up with inches or if something didn't cancel out, I'd have to look at my setup and make sure I did my algebra correctly, okay? So that's number one, why I want to make sure that you use the units all the way through. The second thing that we have happen here. Now, and this will become more and more evident as we do more problems. Notice that I ended up with a positive value for my final answer, okay? Positive value for my final answer. That does not dictate if it's going up, down, left, or right. It just means that whatever direction I assumed was correct. Because in the original diagram, I showed this going up, all right? And I just put it there. I didn't even really talk to you guys about why I did it. We just put it going up. And in some cases, you might be like, yeah, that makes sense. But to confirm if that direction is right or not, your final answer has to be positive. You never leave a final answer for a reaction force as a negative. If you end up with a negative value, you need to change the direction to opposite of whatever you had here. We will see this play out because I do it intentionally in a couple places, but final answers will always be positive. You never hand in anything with a negative final answer, okay? Now that we have our BY here, now we can go back up to the sum of the forces in the Y equation and we can substitute to 2350 pounds there and solve for AY. So now I can say that AY plus 2350 pounds is equal to 3,000 pounds. Subtract that on both sides. AY is going to be equal to 650 pounds. Now again, notice that my AY was a positive value. If I would have plugged this in and it would have gone to a negative value, then that would have meant that the direction that I assumed was incorrect, and I would have to change that direction, okay? Positive final answers confirm the direction that you showed it in. Even though these two are going up, which is positive for our convention, we assign those in the original problem, like in the original sum of the forces, okay? This final answer doesn't say, oh, it's positive, it's going up. It just says we're confirming the direction that you assumed. So if this was going down and I got a positive value at the end, that just meant that my down was correct. Okay. We'll continue to reinforce that, but I want you thinking in those terms right away. Number one, are my units coming out appropriately? And number two, do I have a positive final answer confirming the directions I assumed? Okay. Because sometimes you don't know. There are cases where it's like, know which way, but just assume a direction. All right, any questions on this one? So as we look here, we've done bits and pieces of this all the way up to where we've been. We've done some of the forces in the X and Y equals 0. The only thing that we haven't done yet is moments equal 0, but I think that's not a far stretch because we've already summed moments in our previous module. So we're just applying. All right, let's do another example. Let's look at problem 4.3 on the same page. So it's the very next problem that we see here. Here we have a gardener that uses a 16 Newton wheelbarrow to transport 250 Newton bag of fertilizer. What force must she exert on each one of the handles? Okay, so you're going to see that they're giving us our distances here horizontally for all of the items. We have the 60 pounds coming down. They're giving us the distance from the center of the wheel to that, and then the distance to the center of gravity for our fertilizer, and then the distance to where she is supporting or holding up the handles. So again, we're going to start with a free body diagram in our convention. And then we're going to kind of identify all the different elements. So I'm going to start with my convention in the upper right-hand corner. Okay, right there. And then free body diagram wise, we're going to do it just like we did our last one. We're simply going to draw a horizontal line. Now, in this case, they don't, oh, they do. They give a letter for the center of the front of the wheelbarrow wheel. So this is going to be point A. And then we have 60 newtons. We have 250 newtons. So I'm going to put those here. So the 60 newtons is the weight of the wheelbarrow. And the 250 newtons is the weight of the fertilizer. And then we'll just call this point B. This is going to be where she is holding on to the handle. Now, you might say, but this is kind of at an angle. How come you're not showing these at an angle? Why are they straight lines? Well, remember, per the principle of transmissibility, we can move these forces anywhere along their line of action, and it'll still have the same net effect on the body. So if I start at A here and I draw a horizontal line, I'm just moving these down, okay, and up. So I'm not violating anything. We're still okay. And then I'm going to add the distances that they give us here. So the first one is 0.15 meters between A and the 60 newtons. Then another 0.15 meters to the fertilizer, and then 0.7 meters to the end. So I think that adds up to 1 meter. So these are what I would call our applied loads, the loads that we know, the weight of the wheelbarrow and the weight of the fertilizer. Now we want to put in our support, our reactions at our supports. So the first support is going to be the wheel in the front. We want to identify the type of support that is. So if we look here, what kind of support do you think? I've got fixed support, no. Frictionless pin, I think so. It's a roller again, isn't it? Yep. So roller, we're going to have one force, and it is going to be perpendicular to the surface it's riding on. So since we've got two forces going down here, I think it's pretty safe to say that at A, we are going to have a vertical force, and I'm going to call that AY. The other support that we have is the person who is holding on to the handles, okay? This really doesn't reflect any of the supports that we are seeing here, but it is going to be like the roller because inevitably it's allowed to move horizontally, but she's lifting it horizontally or vertically. So we are simply going to show it as a very similar force here to AY. This is going to be BY. Okay. All right. Do we have everything that we know, I think, for the free body diagram, right? We've got distances, we've got the labels, we've got our units, we've got the two supports represented by forces in the directions we think they're going to go. So we should be ready to use our equations of equilibrium to solve for the unknowns. Now, remember, we have three equations of equilibrium. Which one are we not going to use? Some of the forces in the x equals 0, exactly, because there are no horizontal forces in this example. Don't worry, we'll get it. We're starting out with just verticals right now. So yes, we're going to use two equations of equilibrium. One is going to be the sum of the forces in the y equals 0, and the other one is going to be sum the moments equal to 0 as well. So which one do we want to start with? Anyone? Did I hear sum the forces in the y? I don't know if I heard something. I feel like I might have. Yeah, I think I did. I think I did. That's what we'll do. I think that's a great place to start. So let's sum our forces in the y direction equal to 0. So you have to tell me you're going to do that. And now we're going to, right below it, do that. All right. So I'm going to start left to right. I've got a positive AY, negative 60 newtons, negative 250 newtons, and a positive BY. That's my sum of my forces in the y direction. I'm going to set that equal to 0. Then I'm going to combine what I can. Looks like I can combine my -60 and my negative 250. So that's going to be a negative 310 plus AY plus BY equal to 0. And then I'm just going to put that 310 over on the other side. AY plus BY is equal to 310 newtons. And we have to stop there, right? That's okay. We've got two unknowns. We can't go any further. So the other equation that we have is sum the moments, right? Now, our unknowns are at A and B. So of those two, where do we want to sum our moments around? Is either one better than the other? No, no. So you're going to notice that I tend to start on the left-hand side more often than not. So we'll sum moments around. Now, let's do moments around B just for the heck of it, right? Let's like go out of our comfort zone. Try something new today. So we're going to sum our moments around B. So that means that our two unknowns are AY and BY. And by doing that, if I push in the direction of BY, it's not going to cause a rotation. So that means I only have one left over. So I'm going to let you write your moment equation. I think you can do this because we've been practicing moments in module 4. I'm going to leave a little space here because I know I'm going to have to come up and do a little substitution. But I'm going to sum my moment around B equal to 0. So go ahead and fill it in, and then I'm going to follow in just a bit. Go ahead and finish up and see if you can solve for AY, and then I'll do it together and we can just check our work. All right, I'm going to start writing mine. So I'm going to put my finger on B. That eliminates BY. I'm going to go in the direction of the 250. This is going to go counterclockwise. So I'm going to have 250 newtons times perpendicular distance is 0.7 meters. And then again, it's going to go counterclockwise. So that'll be positive out front. My next one is going to be my 60 newtons. Okay. That's also going to be counterclockwise. 60 newtons times 0.7 plus 0.15. So 60 newtons times 0.85 meters. And that's going to be a positive out front as well because it's counterclockwise. And then my last one is going to be my AY. That's going to be clockwise. So that'll be a negative moment. AY times 1 meter. So negative out front, AY times 1 meter. Okay. Equal to 0. All right. Now what I can do, I can see I only have the one unknown. I can multiply and combine the first two moments. So 250 times 0.7, that is 175 Newton meters. Remember, it's not newtons per meter. We're multiplying newtons times meters plus 60 times 0.85. So 51 Newton meters. Did you guys get those same values? Hopefully. Okay. Just double checking because I'm not putting them in again. Then I've got 1 meter times AY. Now I'm going to combine these two together and move them to the other side. Okay, so they're going to combine to be 226. So I'm going to move them to the other side. They're positive on the left. So I'm going to have negative 1 meter times AY is equal to a negative 226 newtons times meters. Okay, now I have two negatives. What does that do? They both become positives, right? I end up with a positive value. That's a good news because that means what to me? Yes, AY is in the correct direction. Yes, it's going up, but I assumed it going up correctly. That's what the positive number is. Now, dividing by 1 meter, meters cancel. And I look for this. Do you guys cancel things out? Do you combine where they need to be? That's why we're putting our units all the way through. I didn't cross out newtons and I'm solving for a force. It's good news, right? That's what I'm expecting. So AY is going to be 226 newtons. Box around, okay? Now I'm going to take my AY, I'm going to put it back up here and I'm going to solve for BY, okay? So this is going to be 226 newtons plus BY is equal to 310 newtons. So if I take 310 and if I take the 226 and I put it on the other side, my BY is going to be 84 newtons, right? Because this would be a negative 84. Left over is still positive. So that means that I assumed the correct direction for BY as well. All right. These are fun, aren't they? I bet you can't wait to do your homework. I really am excited for you guys. All right. Well, what we're going to do is we're going to do sample problem 4-1. Let's take a break though. So let's take a 15-minute break, come back at about 7 o'clock, and then we will continue the fun.